In this video, we'll discuss lexical closures. But first, a quick recap of some of the important concepts that we've covered in this chapter up till now. So we talked about first-class functions, which is the notion of treating functions as data, and we also talked about higher-order functions, which are those functions that work on other functions as data. So functions that either take another function as an argument or return another function as its value. We also talked about anonymous functions, or lambdas, which are those functions that are defined without being also bound to a name. We talked about lexical scoping earlier on, which says that functions can be defined inside other functions, and the nesting of the scopes of those functions will match the block structure of the code itself. We talked about free variables, which is when we have these nesting of scopes, the free variables are variables that are used in one of those nested scopes but defined in some outer scope, so non-local variables. So at the junction of all of these concepts is the concept of closures, or lexical closures. So think, if a nested function can use free variables from their enclosing scope, so a variable that's defined in some outer function, but that outer function can also return the inner function as its value, right, if we use a lambda. So if we have a lambda that's using a free variable that gets returned out of its native scope, if you will, the scope where it's defined, what happens to those free variables? So what happens when a nested function is returned by its enclosing scope? What happens to the scoping rules there? This is the idea behind closures. So there's two different views. In this video, we'll talk about the functional view of closures. We'll work into the implementation view in the next video. But let's just start with an example. All right, so let's go to Dr. Racket, and let's just try out an example here. So just the same code out of the slides here, but type it out, multiply by, and this is just some variable x. And the body of this is a lambda, takes in a variable y, and says times xy. So presumably a simple function other than maybe that lambda in the middle. And then I'm going to define two other things here. Double to be multiply by 2, and define triple to be multiply by 3. Okay. So first things first, if I run this code, it's going to define this function multiply by, and then it's going to define double and triple as the value that comes out of multiply by when we pass in the value 2 or when we pass in the value 3. So first question you need to ask yourself is, what type of value are double and triple? And if I ask Dr. Racket that, what is the value of double? It's a procedure object. Same thing with triple, presumably. It's a procedure object. Now, if we look at the body of multiply by, the entire body of this is just a lambda. So what we're doing is we're passing in a 2 into multiply by here. We're making that function call with the value 2. That goes into x, and then all it does is it returns a lambda. So lambda y times xy gets bound to double and triple. So we have this free variable x inside this lambda, but the lambda is not executed inside multiply by. The lambda is executed presumably out here. We'd say something like double 2 or triple 5. Okay, so presumably double 2 should be 4, and presumably triple 5 should be 15. But yeah, so if we have this variable x, this free variable x, if we're inside the scope of this lambda, and we ask what's the value of x, we don't find it locally, so we go looking into the enclosing scope and we find it there, which makes perfect sense with lexical scoping if we're running that lambda inside this nested multiply by scope. But we're not doing that. Instead, multiply by is going to return that lambda out into the global scope, we'll call it double, and then we'll run that lambda out here in the global scope. So what happens to that free variable x? Well, let's run our code here. We get the answers that we're expecting, so presumably that variable x still has its value. The procedures double and triple here, or the lambda that they're representing, they seem to remember the values of their free variables. Now we have different instances of multiply by, so we have different instances of x, so we could say the different instances of a procedure remember the values of their free variables. In terms of an analogy, think if I had some sort of programmable smart device, like let's say an Alexa or a Google Home or whatever, whoever wants to pay me to advertise their product here. If I asked it, what's my name? It would presumably say, Andrew. Your name is Andrew because it's my Alexa, so it's what I programmed it to say. Then if I handed that same device to you and you asked it the same question, what's my name, it should still say Andrew because it's my Alexa. And I gave it to you, but it still knows, or it's still programmed with my name. Okay. This is the idea behind lexical closures. A lexical closure is a function that's bundled together with its environment. Remember, the environment is just essentially the collection of all the bindings that are visible at a given point in our code. So the given point in the code here would be the body of this lambda. So the scope of this lambda and all of its enclosing scopes constitutes the environment that we would run that lambda in. So when we create a function, when we execute this lambda to get the procedure object itself, it bundles together all of the information it needs to run that procedure, as well as the information about its environment, the context of that procedure. Okay, so it's as though a function remembers the value of its free variables even after it leaves its enclosing scope. Now, from a purely functional programming point of view, free variables can just be substituted for their values at function definition. This is because we have that idea that the variables are all constant. Okay, we have referential transparency, which means that the values of variables, the symbols for variables can be replaced by their values without changing the meaning of our code. Okay, so from a purely functional point of view, it's as though when we created this lambda, as soon as we had a value for x, we substituted that value into the body of that lambda, and what we returned was a lambda y, where this x was either a 2 or a 3. Actually, let's just walk through the substitution model here. So if I said, for example, let's say triple 5. So triple 5, the value of triple is just a function or procedure object, which we saw, and 5 is an integer. So we're ready to do the application step, which says pass 5 into the body of triple. Remember, triple is just a stand-in for this lambda here. So the body of triple is this here, where we have 5 substituted in for y. But before we got to this line, up in the define stage, or we'll say, line 5 here, we said something along the lines of define triple to be multiply by 3. What that says is figure out what the value of multiply by is. So apply multiply by to the value 3, which says take the body of multiply by and substitute the value 3 for the parameter x. So in the body of multiply by, we substitute the value 3 for the parameter x. Then later on, when we say triple 5, the body of triple has a 3 in there instead of an x. So when we say triple 5, we're just substituting the body of triple looks something like this initially. 5 gets substituted in for y, and we have just a simple expression. It should give us 15. Okay, so from a purely functional point of view, we can just think of the substitution model as being canon. That's what happens. It takes the value of whatever argument, so here let's say, whatever argument we're passing into multiply by, the value 3 goes into x, and it gets substituted right away throughout the entire body. If we're going to assume all our variables are constant, that won't lead us astray. So if we can assume referential transparency, this functional view of lexical closures makes sense. All right, let's do a quick practice example, make sure all that made sense. So I'm going to type out another lambda expression here. So lambda A, lambda B, C, and then just something simple. If greater than the difference between B and C, A, then pizza, otherwise French fries. Okay, nice nonsensical example here. 3 close brackets to round everything out. So, what is the value of this expression? If I were to run this, what would the output be? Again, pause your code, pause the video, try and understand the code without running it, and see if you can figure out what's the output of this expression. All right, so let's try it out. So if I run my code here, we just get a procedure, right? So in this case, we haven't actually done anything. The entire expression starts with the lambda, so that's your first clue that this whole thing is going to return a procedure, because the outermost function is just a lambda, and lambdas create procedures, so the rest of this stuff is what happens when we run that lambda. So if we want to run that lambda, we need to wrap it in another set of brackets. So let's wrap this in a set of brackets. And now, how many parameters is this lambda expecting? So there's 2 different lambdas here. We got lambda A and lambda BC. But because this lambda A is the outside function, or the first function to be observed, the first special form. I shouldn't call lambda a function. Because it's the first lambda, that's the one that's going to get executed. It's the outermost. So in this case, we have one parameter, the letter A. Or sorry, the symbol A. So let's give it a value. How about 5? All right, now if I were to run this code, now what is the output? Well, let's try it out. So we run the code here, and we get a procedure again. So specifically, we gave the value 5 to the parameter A here, and that says run this lambda. Now the body of this lambda is, let's put a space so we can highlight just that. This is the body of lambda A, if you want to call it that. So the first lambda just returns a second lambda, a nested lambda, if you will. Now that nested lambda has parameters B and C, so we need 2 more arguments in this case. So if I wanted to print pizza, for example, I should find a set of arguments for this if statement that makes this condition true. Specifically something where the difference between B and C is greater than the value A. So if the value A is 5, then the 2 arguments here, if I wanted to print pizza, should be something where B is at least 5 greater than C. So we'll say 11 and 5. And brackets for the whole thing. So let's make this a little bit bigger so we can see it all. So we have lambda A here. Takes in the argument 5, returns lambda BC here, so then all of this highlighted bit is what gets returned by lambda A, which is the procedure for lambda BC. So what we do then is we take that whole thing, we pass it 11 into B, 5 into C, 11 minus 5 should be 6, 6 is greater than A, which was also 5, so it should print pizza, or rather return pizza. And there you go. So again, we have free variables and closures and all these things sort of being returned. This is a bit more of a nested type example. It's not as clear without the syntactic abstraction of labeling all our variables, but symbolic abstraction of labeling all our functions and symbols, but hopefully that still makes sense. So a lambda can return another lambda, and we just need to provide arguments every time we want to run them. So the term lexical closure technically refers to the data structure that holds the procedure object itself, specifically bundling it together with its context or its environment. But you'll most often hear someone refer to the notion of lexical closures when they're talking about one function returning another function. So specifically in this situation where the scopes don't match the structure of our code anymore because they're moving throughout our code. So one place where we can make good use of closures is in partial application. So a partially applied function is one where we provide some of the arguments now, and we get back a function that takes the remaining arguments. Okay, so it's this idea that we're going to provide some values, and then we'll get back this lambda that has free variables that are using those values we initially supplied, but waiting for new values as well. So we saw an example of this already, the multiply by example for here. Multiply by takes in one value x and one value y. So multiplication itself, just the general idea of times x, y, takes in 2 parameters typically, but this multiply by function is a higher order function because it takes in a single parameter and returns a lambda that's waiting for that second parameter. So we've done some of the multiplication. We've partially applied multiplication to its arguments. We've said, well, here's the value for x. When we said multiply by 2, we said x is 2. So multiply by 3, we've partially applied multiplication to the value 3. But what we get back is this lambda waiting for the remaining arguments or the remaining values. Once we have those, then we can actually do the full application or the rest of the application to get our actual multiplication answer. So the idea here is we can design one function that captures a general pattern and returns functions that compute specific instances of that pattern. Okay, so by constructing one function that returns another function, that higher order or outer function, like multiply by in this example, becomes a generator of functions, whereas the returned inner function is a specific instance of that general class, right? In the case of multiply by, it could return all sorts of functions multiplying by 2 or multiplying by 3, multiplying by 4. By partially applying it to the values 2 and 3 here, what we end up with is our lambdas that are partially applied to those things that are able to compute specific instances of multiplication, specifically doubling things or tripling things, respectively. So let's see a slightly more practical example here. Let's talk about boxcar functions. So a boxcar function is it's a type of function, so x-y map, if you will. It has a y-axis of 0 for most of its number line, but then a fixed constant for some small range of that number line. So it kind of looks like a straight line, then it jumps up and goes straight, and then it jumps back down to 0 for the rest of infinity. So we can create a boxcar code pretty straightforward, or a function that will compute boxcar points for us. So we could say define boxcar, and we need 3 pieces of information. We need the height for how tall that spike in the boxcar should be, and a range for where that spike should be in the infinite number line. So we'll say height, a, and b as the 3 arguments. Now, if we want to compute the value of a boxcar function at a specific point, we still need that specific point. So we can't use this version of our boxcar, which just takes in the general structure of the function. We can't use that to compute specific points, but we can return a lambda that expects an x value and returns the corresponding y value based on the structure of that boxcar. So for example, this would just be if x is within the range between a and b, then we'll return the height. If it's not, then we'll return 0. So, and less than or equal to x, or sorry, a, if x is greater than or equal to a, and if it's less than or equal to b, so if it's between a and b inclusive, then we will say height, otherwise we'll say 0. Okay, so this boxcar function, this outer function here, is a partial application of the entire notion of a boxcar function, because we have some height, we have some range of values, but what it gives us back is a lambda that will then tell us the specific height or the specific y value for any given x value in this function. So for example, let's create an instance of this boxcar. So say define box1 as boxcar that has a height of 10 between the values 3 and 7 on the number line. So from 0 to 3, or from negative infinity to 3, it's at 0. From 3 to 7, it has a height of 10. And then for the rest of negative, or all the way to positive infinity from 7, it's 0 again. Okay. So if we run this, the value associated with box 1 is a procedure, specifically this lambda here. A lambda that's waiting for an x value somewhere on this boxcar function line. So if I said box 1 at, let's say, 10, and ran this, that's 0 because 10 is not between 3 and 7. If I said boxcar 1 at 5, we could run this, and it has a value of 10 because it is between 3 and 7. Okay, so we can get specific values out of this. So we have a partially applied function here. Now what comes out of this boxcar function then are instances of boxcars. And these things are used for signal processing. It's a way of zeroing out most of a signal line and just maxing out or maintaining some range over some small part of that signal line. But that's not terribly useful. The whole point here, though, is that we have a partially applied function. This boxcar thing effectively describes an entire function line, so function in the mathematical sense, and it does so by using a procedure or a function in the computer science sense, where it returns a lambda that takes in a value x and computes the corresponding value y based on the inputs that we've constructed that lambda with, or partially applied to that lambda, if you will. So let's actually see this. So what I'm going to do here is not part of Scheme. I'm going to require the plot library. And this is out of Dr. Racket, so this is borrowed from Racket, not Scheme, just so we know that. Okay. So we've defined an instance of the boxcar. We can get specific values, but let's see what this looks like. So the nice thing about this plot is that it takes in other functions. So something like keyword plot, and then keyword function. So we're going to pass in this box function that we're using, so this box line, this specific instance of a boxcar, and some range of values on which to plot it. So we'll say from 0 to 20 we want to draw this thing. Since the spike is between 3 and 7, we want that in the middle here. That should give us a pretty good view. So let's run this and see what happens. Might take a second. hasn't imported this library in a while, so it might take a second to find it, but there we go. So again, this is from Dr. Racket. Scheme doesn't have nearly so many nice features, but Dr. Racket has this plotting library that takes in some function. Now this function has to have only a single parameter that's used as the x parameter in drawing the function itself, and then some range of values on which to draw. So between 0 and 20, this is our box 1 line. So it goes up to 3, jumps to 10, jumps back down at 7, and continues at 0 for everywhere else. So what we have here is a partially applied function. So box 1 here is partially applied because it has information about the height and the range for which it's active, but it doesn't have any information about specific points. Well, we're going to use that partially applied function by passing it into this plot function, which will supply all of those x points. It'll supply a point for 0 and see it's 0. A point for 1, see it's 1, 2, see it's 2, or sorry, 1, 2, 3, all the way up to 3 here. It'll be 0. As soon as it gets to 3, it starts to jump up at 10, and then back down at, I guess that'd be 8, 5, 6, 7, and then onward from there continues at 0. So it's going to pass in individual x values by essentially calling this box 1 function over and over and over again with all those different possible values. All right, we could of course run another boxcar. Plot's not limited to just this. So the whole point of having these partially applied functions is that our boxcar function, the boxcar procedure I'll call it, just to distinguish between mathematical functions. The boxcar procedure takes in information and generates new boxcar functions. So say between 5 and 10, let's say. So from 5 to 10, our boxcar will have a height of 25, everywhere else at 0, and let's plot that between 0 and 20 is still good. Let's run this one. I'll have to draw them both, so it might take another minute. But the idea here is our boxcar function, this boxcar HAB, sorry, our boxcar procedure. It's a generator for other procedures, so we can create as many different boxcars as we want using this exact pattern. And the same idea is true for any type of partially applied function we can think of. If we can create a higher order function that can distill down just the pattern of what it means to do that thing, in this case what it means to be a boxcar function, then we can create a lambda that needs that extra information to compute specific instances of that function, in this case specific points on this line. All right, so let's do a few more practice examples here, make sure we all understand. So let's start with define foo of f. And foo will do a lambda here, so lambda x, and lambda x will do a lambda y, and lambda y will say lambda z, and lambda z will finally say f of x, y, z. Okay, so if I were to run foo of something, well, foo has a parameter f here, and the name f might be your first indication what sort of type should go into this parameter. But if we look into the body of foo, we got a bunch of lambdas, but way nested down here we have f of x, y, z, so this is where the parameter ultimately gets used. It's not hidden in any of the enclosing scopes, so it's a free variable down here, but it should still be the same one. We can see it's used as the first element in a combination. So the thing that we pass into foo needs to be a procedure. So let's pass in plus. It's a nice simple procedure. All right, so if I were to run this expression, foo of plus, what will the value of this expression be? And if we run it, I should probably comment out the plots going forward. But if we run it, we can see we got a procedure as our answer. Specifically, we get the procedure lambda x. So lambda x needs one argument here. So a good argument, we can see it's eventually going to be used under the plus symbol here. So we can say foo of plus, and then we'll wrap that in a set of brackets and apply the thing that came out of here, the lambda x, to the value, let's say 1. Okay? And if I run this, we again get a procedure, this time the lambda y. So we can wrap in another set of brackets. So we say foo of plus at 1, that's for x, and that returns lambda y. So this highlighted bit here is the procedure that comes out of lambda y. So we'll pass in a value for y into that procedure to see what that happens, or what that does. So if we run this, we get yet another procedure, this time the lambda z procedure. So run this again, so we get foo plus 1 for x, 2 for y, and to follow the pattern we say 3 for z. Now if we run this, this is the last lambda in the body of foo, so the body of z says apply f to x, y, and z. So we can run this, and we should finally get an answer. 1 plus 2 plus 3 gives us 6, or rather plus applied to the values 1, 2, and 3. Okay. So that's a fun example. Let's apply this to a slightly more complex function here. If I say define bar of x, y, and z, and then bar will say minus times x, y, z. Okay. Now if I were to run foo of bar, what would we expect the output to be? So again, we're passing bar into foo as the argument. So it should be given the name f here. And the body of foo is just still a lambda, so we haven't provided anything for the x, y, or z lambda. So if we run bar here, or sorry, if we run foo on bar here, we're still just going to get lambda x. It's a procedure waiting for some information. So as we just saw, if we want to run this, we have to give it some more information. So we'll say foo of bar, and then we'll wrap that in some brackets. Looks like enough brackets. 3, 4, and 5. So if foo of bar gives us the lambda x, why is that not highlighting? There we go. If foo of bar gives us the lambda x, then we provide 3 into that x. That'll give us lambda y, so that's this whole block here. So if we provide 4 into that y, then it's going to return lambda z. So if we provide a 5 into that z, then it's going to run through the actual body of this. So at this point it'll say apply bar to the values 3, 4, and 5. So the body of bar, where x is 3, y is 4, z is 5. Those letters could have obviously been something else, A, B, and C, or whatever you wanted to call them. There's no correlation between that and the lambda letters here. But in this case, they have 1-to-1 as it works out. So 3 goes into x, 4 goes into y, and 5 goes into z, just via this foo function. And then we do the math. So 3 times 4 gives us 12, minus 5 should be 7. We run this, and we get 7 as our answer. So this foo function here is what's called a curry function. It transforms functions that have multiple inputs, like bar, or like potentially the plus operation, into a series of functions where each one of those functions has a single input. Now the reason for having currying functions like this is not super useful in Scheme anymore, but in the original lambda calculus, functions were only ever allowed to have a single argument. Or a single parameter, as it were. So the idea behind having these curried functions is it proves that functions that have multiple inputs can be constructed out of functions that have only singular inputs. So all the theorems that they proved in the lambda calculus relating to functions with singular inputs can be applied to functions with multiple inputs as well. Yeah, okay, let's do one more example here. So, define func of A, lambda takes in B, returns a lambda CD, and then some work inside this. So times B, C, and then a D, close all of those, a couple more closes, close that, plus a 3. Okay, so one big happy function. So here's a good one to pause the video on. If I ask what's the value of func at 1, so if we call func with the value 1 for A, what is the value of this expression? Okay, so let's work through this. So if 1 goes into A, the body of func is all of this expression here. So it's one big combination where the first element of that combination is all of the lambdas, and the second element of that combination is plus a 3, which is to say this outer lambda, lambda B let's call it, gets applied to whatever this combination evaluates to. So if we evaluate this, we get a procedure that's expecting a single argument for B, and if we evaluate this with A having the value 1, we should get the number 4, so we're going to apply lambda B to the value 4. Okay, the body of lambda B then is lambda CD. Okay, so if that's the entire body of lambda B, notice it's only a single set of brackets, it's not being applied to anything, then when we apply lambda B to the value 4, what we get back is a procedure object, and that's the value of this entire expression, is a procedure object. So if we run this, we get a procedure object. Okay. So specifically, the procedure object we get back is this lambda CD. So lambda B here is applied inside the body of func, and it returns a new lambda that is not applied yet. Okay, specifically though, we get a closure. So closure in the sense that it's a function being returned that has access to free variables. The free variables b and a if it needed it, although it's not using a here. Okay, so just the free variable b then. But if we're outside in the world here, let's run this a slightly different way. If I said define closure, let's just give it a meaningful name, func1. Now if we run this and we ask what's the value of closure, it's the exact same thing we just saw. It is that procedure, specifically the lambda cd here. So if we want to run closure, if it's a procedure, we need to apply it to things. So we'd say closure, and we give it two values, one for c and one for d. So if I say 2, 3, what's the value of this expression now? Okay, so 2 goes into c, 3 goes into d. We walk through the body of this, where we have a free variable b here, which has the value from the enclosing scope here, which we saw was taken from this expression, which was ultimately a 4 because a was set to 1. All right, so closure 2, 3 says c is 2, d is 3. We get 2 times 4, which is 8, minus 3 should give us 5. And we get 5. Wonderful. And it's worth pointing out here that running it as closure 2, 3, it's the exact same thing as if we had said func1 and then immediately wrap that into 2, 3, right? We didn't have to give it a name at any point there. This lambda could have remained anonymous, and we can still just use it as the return. When we call func1, that returns that lambda. We'll then immediately apply it to 2, 3 and get our value that way as well. So closures, or lexical closures, is this notion that every time a function is created, it needs to be created with a context, with its environment, so that we can keep track of the free variables that that function should still have access to. Now, the free variables are still as we know them. They come from the enclosing scopes or the enclosing lexical blocks, so it matches the nesting of blocks in our code itself. Now, once we have functions that can return other functions, so once we have higher order functions returning nested functions that happen to be making use of free variables, then we had to worry about that notion that these things are being created with, that these functions are being created with their context. So that when, for example, lambda cd gets returned out of its enclosing function, we still have access to its free variables when we call it down here. So when we say closure 2, 3, it runs through the body of this lambda cd, and the variable b still has meaning. Even though it's now left the context, it's not being run on this line, it's being run out in the global scope, the closure function itself, or the thing that refers to, this procedure object here, is created. It has essentially enough information to point to all the work that needs to be done, as well as the environment in which to do that work, an environment that has the free variable bindings relevant or accessible to that execution. Okay, that's it for this video. In the next video, we'll move into talking briefly about the implementation view of closures and see what closures do to our call stack.